So we will continue discussing the Couette flow worksheet. So I hope you have one. Somebody said you don't have. Would it be helpful if I just post the file quickly? Okay. So I'll just briefly post the file. Excuse me while I'm posting, so I'm gonna do. So if you have slides, I haven't. Okay, I will make that up. So right now I will not go create PDFs so we don't waste the time, but the moment I get back to my office I'll post. And videos, I posted them all. I don't think I sent an announcement, but they are all on YouTube. So if you go check my YouTube channel, you will see videos. So let me upload here. This is the wrong. So all videos should be up there. I'm a little, I think I forgot to post the slides and the things that I've been writing in class. I will correct that. And interestingly enough, nobody said anything, probably because you had a test, so nobody paid attention to. Just a second, let's do by kind. There we go. All right. So it says worksheet Couette flow. All right. All right. So just briefly, what you should have gotten in part A is that V theta of R is C1R plus C2 over R. So I have only one velocity that I'm actually solving for, that's V theta, that's this rotational component, okay? And that velocity component depends only on one coordinate, and that is R. More likely than not, any problem that you can solve by hand will be like that. You will have only one velocity component that is alive, and it depends only on one coordinate. And in that case, you're actually able to decouple the partial differential equation into ultimately an ordinary differential equation that you can solve. We will start, if not today, the next time, the process of solving the flow around the sphere where we are unable to do that, and we have two velocities depending on two coordinates. And it's going to take us through 3 to 4 class periods to solve that problem, okay? To develop the theory, which is called streamline functions, that is actually allowing us to solve for that, okay? So you will appreciate these problems that there is only one velocity dependent on one coordinate a little more, okay? So literally it's going to take us 3 to 4, I believe, so minimum a week, if not longer, to actually develop everything we need to solve for velocity, slow flow around the sphere, okay? So this velocity V theta is V theta of R, and then one puts the boundary conditions in place to actually get the distribution itself. So velocity at the inner cylinder is 0, and velocity at the outer cylinder is this angular velocity. Angular velocity by itself doesn't have a length, so basically you have to multiply it by the radius at which it acts to actually get the linear velocity version. And of course, when you have the constant angular velocity, this particle here versus this particle here, they will traverse different linear distances in the same time, and that's basically the scaling that I wrote here. So once I do that, this is just now things that you can easily work out, that there's no point spending in class and time unless I expected you to finish it. And basically you can get something, I'm gonna write it in a specific form that is kind of normalized version form the textbook prefers. R divided by kappa R minus kappa R over 1 over kappa minus kappa. So the reason to write in this form is essentially you can see the relative, this is sort of a normalized radius, if you will, and it's normalized with respect to the inner radius. So that way you kind of eyeball immediately where you are in between these two cylinders. All right, so this is the velocity profile, okay? And basically, if I actually applied in C and D, I asked you to basically simplify R and Z equations, and if you do that, you should get minus rho V theta squared over R is minus dP dr. So basically your pressure depends on angular velocity, so you can go and integrate this if you like. And the Z equation is minus dP dz plus rho g is equal to 0. We're mostly interested in velocity distribution here, so I'm not going to actually go solve for pressure. And the reason why I want to solve for velocity is that I actually want to solve for the following problem. This Couette flow is actually the basis of Couette viscosimeter. So the way we will actually, at steady state flow, okay, there is, if I'm imposing a steady state flow on this viscosimeter, I can actually measure basically what does it take to keep that steady state, right? So I can measure things from the outside. And at steady state, I also know the balance of forces. So I can actually find the force on the outer cylinder, okay? That is the force exerted by the fluid on the outer cylinder. And I can balance that with whatever outside conditions I'm actually putting in place to rotate that cylinder at that steady state. And comparison of the two will actually give me viscosity. So I will be able to compute viscosity. Now viscosity, interestingly enough, does not actually play a role in velocity distribution, which is different from the viscosity profile in the tube, right? In the tube, I actually had viscosity coefficient as part of my distribution. Here it doesn't. Okay? And that's somewhat in part to the boundary, because of the boundary conditions as they're imposed. Okay? If they were maybe both 0 something and I was flowing in z direction, then yes, I would have viscosity dependence, but in this case, I don't. So let's actually compute this force so we can actually do the balance. So if I have the outer cylinder, okay, I'm interested in the total force exerted by the fluid on the outer cylinder. I could also do the similar calculation for the inner cylinder, and those two would balance. So basically, the force I will have, because I have this theta velocity, okay, what is the shear stress that I should be looking at? I have my fluid, which is in the region that is less than R is equal to uppercase R, right? And that fluid is exerting basically the force on the cylinder, right? And the velocity itself is in theta direction. So what is the shear stress that I need to be looking at? Tau R theta. So basically my tau R theta is force. Force is in which direction? Theta direction, right? That's my velocity direction. exerted by the fluid in the lower R, okay, with respect to that solid, onto the solid, onto the surface or fluid in upper R. Okay. And what is my tau R theta? Where am I going to look up that? In appendix, there's a formula for cylindrical coordinate systems. So please go to appendix B1. And it's B1 what? Who has the book? B1? 11? So it's minus mu and then what? I know minus mu part. R ddr v theta over r plus d theta. Okay. Well, there is no theta dependence and there's no VR, so this is 0. So I'm left with this part. Okay. I have v theta as a function of r, so this is a simple derivative with respect to r. I'm not going to go through this, I'm just going to say dot, dot, dot. Okay. And you should get minus 2 mu omega 0 kappa square over 1 minus kappa square r over r square, uppercase r over r square. So this is my tau r theta. So it depends only all on r. So it's tau r theta of r. All right. So now what is now if I have a surface element? The total force on a surface element will be tau r theta times the area of that element. So basically, if I have a surface element and I'm looking at the surface, r is equal to r, which is my outer cylinder. Then my force on a surface element is tau r theta evaluated at r is equal to r. Okay. The element area is r d theta dz. So this is my cylinder. Okay. If in doubt, go into Appendix A, where you have cylindrical coordinate system and review. And there's also direction to this force. So if I'm actually looking at the force direction, what is the direction of this force? Theta, right? Tau r theta has theta direction, so does the force. So basically, if I look at the force as a vector, this is the direction. Okay? So don't forget the direction. Though book is guilty of often just presenting you with the force magnitude and not really commenting how they got there. Okay. Now, one thing that I'm actually, when I'm rotating this, so I'm rotating the outer cylinder, okay? And that's what I'm doing from the outside. So I know what work goes into that. And basically so this is rotational movement, so I have to look at the moment of this force, okay? So moment of the force or the tendency to rotate the object is called torque, okay, in this case. And torque is defined as So torque is moment of force or tendency to rotate an object. And torque is one of those things that actually requires definition of a cross product. So if you have what's called an arm, R, and you have force F, then the torque is R cross product F. Do you remember this from physics somewhere? Probably your first or second undergrad year. Maybe some in high school, maybe not. So back in the day, you have defined torque, or this moment, as a cross product. So basically, I'm going to have a different value depending on how long my arm is, right? Okay. So if I'm going to actually look at the total torque on this surface that takes basically to rotate this entire outer cylinder, that's the one I'm rotating, that's integration of this torque, right? Defined of this like over the surface area, okay? So for each surface element, I know what my distance r is from the center. I know what my vector, that's why I needed force as a vector in this case, okay? I need my force as a vector. I need to do cross product of them, and then I integrate that over the entire surface, and that's going to give me the total torque to actually, or moment to rotate this outer cylinder. And that's what I need to do. That's what I need to put in, essentially, to keep this rotation steady state, okay? So actually I have, it's a coefficient times this constant angular velocity that you get, and that value you actually know. So if I compute what torque is, there will be some dependence on viscosity in there, okay? So I will be able to back calculate viscosity from there, okay? So that's basically where we're going, okay? So I'm now going to compute this, and basically I have everything, so it's not a difficult So basically my total torque, I'm going to say T total and outer, okay, is, so basically my arm has radius r and the direction of the vector delta r, right? That's my arm to the point or surface element on the outer surface. Cross product, my F, and my F I said was tau r theta of r. It's in theta direction, my force is shear force. And then my area element is r d theta dz. And I need to integrate that for d theta that goes from 0 to 2p, and dz that goes from 0 to some length L. So I'm assuming I have a length L in z direction, okay? Now, what is vector delta r, identity vector in r direction, cross product d theta? Remember the right-hand side rule, right? So this is going to be the third vector of this coordinate system, right? Which is delta z. Okay, so right-hand side rule. And my delta z is one vector in this coordinate system that actually doesn't depend on location. Okay, so I can actually take this delta z outside of the integral. Delta r and delta theta I cannot by themselves. Okay, just by themselves I cannot, but if their cross product is delta z, I can. So basically this is Now I have delta z, so I don't have dependence on r at all, so I can actually take everything out. Okay. So it's going to be r squared tau r theta of r delta z in 0L 0 to p d theta dz. So this is, of course, 2pl. Okay. So no dependence on theta or z. That's why I can put it outside of the integral. And now when we put this all in, we have expression for tau r theta r. So it's minus 4p mu omega 0 r square L kappa square over 1 minus kappa square, and it's in z direction. The total torque is in z direction. So the actual absolute value or magnitude is this. And I believe textbook just serves you with this. And that is equal to a torsion constant for the basically my experimental setup, or the wire that is basically responsible for rotating it, and that's something that I have because I calibrated my instrument. Okay? So my torsion constant times theta b, so this is angular displacement. And this is a known torsion constant. So it suffices to say that this is something that I know from my instrument. The moment I calibrated the instrument, I have this. So this is something, I have this after calibrating my viscosimeter. So basically, by equating the two, so this equals to this, I can back calculate viscosity. If it's a Newtonian fluid, it's a viscosity. If it's some other fluid, then it's effective viscosity. So I will still use the same formula. So different experimental setups have different viscosimeters. This is a so-called Couette viscosimeter. You could have a capillary viscosimeter as well, in which case you would actually use Hagen-Poiseuille equation that you know. All right. So this basically is our example of Couette flow. Yes?
Is Z defined downwards or upwards in this scenario?
Upwards. I drew the picture at the very beginning.
Didn't that give the torque downwards?
So overall torque has a minus. So yes, it's going to be overall torque will be downwards, but
Given that it's counterclockwise,
I have,
wouldn't we expect it to be upwards?
no, r theta z. So if I'm doing cross of r times, it is counterclockwise, so it would go down, you say? Where's my, r is supposed to be here. If I'm doing r cross theta, okay, then r is supposed to be this way, so then z is pointing upwards. So delta r cross delta theta is delta z. So delta r cross delta theta is pointing upwards. But overall torque does have a minus sign to it, so it's pointing downwards. So, and on the inner side, I would actually, so I could also do this whole procedure on the inner, the stationary. So in that case, I would integrate minus tau r theta because my fluid is in the region of Lassard, so I would get the opposite signs, so they counter each other at steady state. So at steady state, those two forces are in balance. Does that answer your question? Yeah.
Quick question.
Mm-hmm.
Torsion constant is solid or fluid?
It's basically let's assume that you have a wire that is actually connecting the system. So it's basically constant, there is material constant related to whatever setup you have in the lab. And that's something when you are calibrating the setup, you will throw in a couple of, you will throw in a fluid of known viscosity and you will rotate it at different speeds and basically calibrate to get what that is. Right? If you have 3 points on the graph, you can fit it with a straight line, right? And, all right, so now what we will do before we actually move to the floor and the sphere that I introduced, we will just basically summarize. So what we used here as an example, we solved so-called Navier-Stokes equation. So I'm going to write down the equation in vector form and how we get it from the equation of motion. And then I will just outline a couple of other, that's going to be the equation that we use most of the time. And then a couple of other special cases such as Stokes equation, Bernoulli equation, and Euler equation. So basically this is just continuing on our special cases. So this was, we have used tabulated Navier-Stokes equation to solve the problem, Couette flow. Okay. So I mentioned, so my general equation of motion is rho dv dt, that's my mass times acceleration term, okay, or density of it, is equal to gradient in pressure, divergence of shear stress, and outside forces. Now, if I actually, so when I get this as my special cases, the first one is Navier-Stokes. That I get when my rho and mu are both constant. And tau has a special form, which by now you should be able to write down if I wake you up at 2 a.m. And that is minus mu. That part we got. Velocity. Then if I have this one, what else do I have? It's symmetric, so I have transpose in it as well. And that other weird term that we always hope to not have in the equation. So if rho is constant, then as per equation of continuity, I'm going to get that this is 0 as well, right? So for constant row, equation of continuity will give me that divergence of V is 0 as well. Okie dokie. So let's now actually put that all in and see how it simplifies. So one thing that I don't have is that I have to actually basically go and simplify this term. So I'm wondering what is my divergence of tau, and I'm putting these brackets around it because I know that divergence of a tensor is a vector. So brackets indicate the vector. So that is, oh, well, that's minus mu divergence of Jacobian of velocity plus divergence of that same thing transposed. Okay. So what is this term? What is actually gradient of velocity? Let's write it down. It's partial x partial x. Then I do the same partial y, partial vx, partial z. So I repeat everything with Vy. And then with Vz. Oops, not plus. This is Vz. I keep actually on this device, I keep trying to use my finger to erase things. And I wonder if some next iteration of the device will allow for that. Anyway. Otherwise I have to press and... All right. So what did we say is divergence of a tensor? So basically I will have to do, and then a transpose of this is just, of course, transpose. So what is going to be x component of this? Okay, so it's a vector, so it has x, y, and z component. What's going to be x component? Divergence of first column. Okay, so it's divergence of Vx dx. Well, I'm just going to write it as a row vector. I can put a transpose to just say, oh, it's a column, but it doesn't matter. For divergence works equally well on a row vector or a column vector. Right? So how does divergence work? It takes partial x of the first, partial y of the second, and so forth, right? So basically I'm going to have double derivative in x plus partial squared partial y. This is going to be partial y, partial x plus v. Is this supposed to be z? Yes, it's supposed to be z. Okay. Now, assuming nice and continuous and what's called C2 functions, so both twice differentiable and continuous at that, I know that I can actually, this partial v, partial z, partial x is the same as taking partial x, partial z, right? So this entire business here is partial x of what? Partial vx, partial x, plus partial, this was a z, vy, partial y, plus partial vz, partial z. And what is that? Divergence of V. So therefore this is 0. So this part is 0. And guess what? If I did this in y and z, I would get the same. It's all symmetric. So similarly is also 0, and so is z. So basically divergence of v is a 0 vector, right? Okay, so what's going to be now? I need to, so this first term is easy. I basically knocked it out. With second term, won't be that lucky. Did everybody write this down? Can move on? I'll take that as a yes. Silence is acceptance. Okay. So now I actually need, I don't need to write in red. The second term and the x component of it will be divergence of the first column vector of the Jacobian transpose, which is basically the first row of, yeah? So this is first row of gradient, right? Because that's the same thing as first column of the gradient transpose. So that is then am I doing that? No, the other way around. Vx. Right? So this is equal to dx squared plus, it's going to be Vx dy squared, right? Plus Vx dz squared. Everybody agrees with me? Divergence takes partial x of the first, partial plus partial y of the second, and plus partial z of the third component. Okay, so this, there's a name for this. How do we call this? It's a Laplacian. So sometimes it's termed like this, and sometimes it's written like this. It's Laplacian of Vx. So then, of course, if I do this for y and z coordinate, I'm going to get Laplacian of Vx and Vy and Vz. So basically, I can then write that divergence of gradient transpose is, I'm going to adopt this nabla square, Vx, nabla square Vy, nabla square Vz. What am I going to define now to make my writing shorter and my life easier? I'm going to define Laplacian of a vector. Okay? And that's going to be a vector whose coordinates are Laplacian of individual coordinates of that vector. Okay? So this is define Laplacian of V.
Are we going to use that notation for the Laplacian, the square?
Yeah, but you will see both this and this in literature, okay, when writing Navier-Stokes equation. So when you see Laplacian of a vector, just go coordinate by coordinate and do Laplacian coordinate by coordinate, okay? Just like with divergence of a tensor, we did what we could. We went basically column by column. Okay? So Laplacian of a vector works coordinate by coordinate. You kind of go and do what you can. It's a little intuitive, actually. Because normally I know what to do with a scalar function, but with a vector function, I'm going to go with all of the three scalars. All right, so this basically defines Navier-Stokes, or finishes defining. So rho dv dt is minus gradient of p plus mu Laplacian of v plus rho g. And that is actually what is written out coordinate by coordinate in all three coordinate systems in Appendix B. Okay. The simple next example is for a very slow flow. I can assume that acceleration is nearly zero, and that gives me so-called Stokes equation. That has on the left-hand side 0. So basically Stokes equation very slow flow assumes that rho dv dt is approximately 0. And what we solve is minus gradient p plus mu plus rho g is equal to 0. This is most commonly applied in porous media within the actual porous medium. So if you assume a sandstone, the pathways that you're going through have basically 10 to 20 micron, 10 to 60 micron cross radii and diameter, somewhere on that order. So if I have a grain that is 100 to 500 microns in radius, pore spaces neighboring, it will be a fraction of that. Typically you take 1/5 to 1/3 of the actual grain. Okay. So basically the neighboring spaces are also on the micron length scale. So through those spaces you can assume slow flow, so most of the time you're actually going to solve this steady state version of it. Okay, so often solved within rock pore space, basically on pore scale. The moment you're like in a fracture or near wellbore, you have a damage zone, your pore spaces are larger, that's where actually this becomes less and less applicable, and you actually should go to full Navier-Stokes. Third example is on the other spectrum that we basically don't.
You have to have constant viscosity.
Yes, so this is just a special case of Navier-Stokes. So special case. On the other end of the spectrum is a situation where velocities are actually so fast that viscosity has no time to act. Okay? And that is our Euler equation, and that's in aerodynamics, basically solving flow around airplanes. Okay? So that's the part where you can basically ignore the viscosity times Laplacian of velocity. Okay? But you cannot ignore the time component, so basically you will, so this is inviscid fluid where my divergence of the shear stress can be ignored. So my rho dv dt is just minus gradient P plus rho G, or minus gradient generalized pressure. So this is commonly applied in very fast flows in aerodynamics. Needless to say, I haven't seen it much in porous media. And it's called Euler Equation. The solution to this typically has shock waves in it, but you know that from practice of hearing planes going through the sound barrier. All right, and the final one, I will just write it down and then we can just quickly comment it next time. Okay. The final one is Bernoulli equation. This is steady state inviscid, so very simplified equation, irrotational flow, constant rho and mu. And in general vector form, this equation is gradient of 1/2 v squared plus generalized pressure is equal to 0. I'm actually going to write it down as this. So basically 1/2 v squared plus pressure is constant. Most common application was this was when you had flow like this. Okay? So basically you have pressure 1 and velocity 1 here, pressure 2 and velocity 2 here, and then you said that, oh, there was a rho here. So basically there's 1/2 rho v1 squared plus b1 is equal to 1/2 rho v2 squared plus b2. And this is ignoring gravity and assuming just one direction, one velocity direction, right? So I'm going to derive this briefly next time. All right, I see you on Friday.